Well, thank you for coming to a talk late in the afternoon on the last day of the conference. I'm Itai Segev. I'll be talking about changing variables and other calculus tools. So I was thinking about how to organize this talk, and I realized that everything in sort of the main part of my talk is about the chain rule. So implicit differentiation is just the chain rule. The changing variables is in an integral. It's a bit more complicated, but it's basically built upon the chain rule. Changing variables in differential equations, that's even more complicated in all sorts of ways, but fundamentally it all goes back to the chain rule. And this covers three main new functions in version 13.1 that I'll be telling you about. If I have time, I will briefly touch on a couple of features from 13.2 that have nothing to do with the chain rule. But let's dive right in with implicit differentiation. Obviously, this is a core topic in introductory calculus courses. It's a direct application of the chain rule and the implicit function theorem that you don't actually prove until you take real analysis a couple of years later. Implicit D, like we have D for partial differentiation, implicit D does implicit differentiation. You specify the equations, the dependent variables, the independent variables, and optionally, you can give it an expression to differentiate. So let me clarify all that with some examples. So let's differentiate y with respect to x, assuming that y is defined by the formula x squared plus y squared equals 1. So here's my equation. Here's my dependent variable. Here's my independent variable. I differentiate, and I get minus y over x. If I could do the exact same thing, only add the optional first argument, which is the expression to differentiate, and I get the same answer. So let's differentiate y squared under these same conditions, and we get minus 2x, which of course we had to get that because x squared plus y squared is equal to 1. You differentiate that, you get 2x plus the derivative of y squared is equal to 0. So minus 2x. And here we can take higher order derivatives. So here's the second derivative with respect to y. That's just the quotient rule applied to our first derivative. So some slightly fancier examples. We have e to the x plus y along a curve in 3 dimensions defined by 2 equations. So there's that. If we omit the first argument, it'll take our dependent variables, y and z here, and give us the 2 partial derivatives there. So I differentiate and I get that. Here I have 1 function and 2 independent variables. So 1 equation, 1 dependent variable, and I'm going to take the mixed partial derivative. I can also compute the gradient of this function with respect to the 2 variables. Notice that I have a list containing the list xt. That's standard from how D works when you want D to give you a gradient or higher rank derivatives. And voila, there's our gradient. So a nice application example, find the tangents to a curve in 3D. So I have the curve defined as the intersection of these 2 surfaces. So I find the partial of y with respect to x and z with respect to x. The tangent lines are then just given parametrically by the point plus, since the derivative of x with respect to x is 1, t times that tangent vector. Instead of finding equations defining these lines, we'll just create some pretty pictures. So I'll use infinite line in the form base point tangent vector and easily create some points, tangent lines. I'll find some points that lie on the curve using find instance right here. And I just seeded random to give some nice points that will work out. And here's the plot. I'll just very quickly point out. So I have here, I take the curve. It's implicitly defines a region. So I use that region to visualize it. I add on the points and the infinite lines and substitute in the points, and that's how I created my little potato chip here with some tangent lines. And by moving it around, we can see that indeed it does. These are in fact tangents at the points indicated in red. Now you might think it's not smooth somewhere because if you looked at the denominators here, this blows up, but that's actually, again, implicit function theorem. If we look where this denominator gets 0, that's the maximal value of x and y of x at +1 and -1, where y and z are not in fact functions of x because you're doubling back on yourself. And so that's just, if I wanted to get the tangents at that point, I would have to use a different variable to, to get the equation for the tangent lines. All right, so that's implicit differentiation. Now let's talk about IntegrateChangeVariables, which is a function which implements a basic technique that goes by a whole bunch of names: U substitution, the change of variables formula, changing coordinate systems, even the reverse chain rule, because it's integration, so you can't call it the chain rule. It's a very general function. It supports indefinite integrals, definite integrals, region integrals, and in short, all the types of integrals that Mathematica supports. The old variables are inferred from the integral, so you specify the integral you want to look at and the new variables, and the changes can be specified as equations or coordinate systems. So I will, again, have lots of pretty examples. So let's start out with your simplest U substitution, U equals x squared. I have the integral of e to the x squared times x dx, and I make that substitution, and it gives me e to the u over 2. Here's a rational integral, which is classically performed using a trigonometric substitution. I think even Stephen would be able to compute this integral without the help of a computer. And so you activate it and substitute back in for your original variable, and you get arctan of x. So here's we're going to do the integral of 1 in 4 dimensions, i.e. find the volume of some region, and we'll change from Cartesian to hyperspherical coordinates. And it gives us r cubed sine theta sine of psi squared, along with the appropriate assumptions on the different coordinates. We can verify this directly using the change of variables formula, which tells us we need to take our integrand and multiply it by the absolute value of the Jacobian determinant. And we compute that, and voila, there's our Jacobian determinant, which is in fact positive because of the ranges of the variables, so we don't need the absolute value there. And in this particular special case, because we're starting from Cartesian coordinates, this is also the volume factor property of the named coordinate system. So we look that up, and hyperspherical coordinates does in fact give that to us. So that's indefinite integrations. Here's some definite integrals. So another trigonometric substitution for a rational function. It converted the integral and the endpoint, the integrand and the endpoints. I at least can do this integral without the help of Mathematica. That's minus cosine theta. Substitute in the endpoints, and we get 1. We'll verify the result by just evaluating the original integral. Now I'm going to change from this complicated looking integral from cylindrical to spherical coordinates. And I'll let it think. And while I'll point out the name clash. So we have a theta over here, which is the angle in the plane, and a theta in spherical coordinates, which is the angle from the z-axis. So they're very much not the same theta. So I, in fact, had to rename this theta theta s. If you try to put a theta there, it will yell at you that you can't have the same variable names in both the old and new system, because then you will get very confused. And let's activate that integral. We get an answer. And again, we verify the answer by activating the original integral. And voila, it's the same answer. We can understand this integral by, again, looking at the Jacobian determinant. It's just rho. And so we had, rho is the radial distance from the origin. Here's r squared plus z squared. That's also the distance from the origin. So that's 2 powers of rho. Then we have an r squared, and that's going to be rho squared sine theta, sine squared theta, which, and so you add up all those powers of rho and sine of theta, and we did in fact get the correct answer. We can also understand this answer geometrically. So that's good. So a classical application of this kind of change of variables is computing the Gaussian integral, the integral from minus infinity to infinity of the exponential of minus x squared. So, you know, there's our integral. It's really hard. So the trick is to instead look at the integral of squared. And since x is just the dummy variable, in the second integral, we can call it y, and then combine the e to the minus x squared and the e to the minus y squared. And then you're going to change from Cartesian to polar coordinates. Again, the theta integral has become really easy, just 2 pi, and we'll apply a u substitution. In fact, it's up, except for the minus sign, it's basically the same u substitution I did in this talk. And we do the integral and apply the fundamental theorem of calculus. That gives us pi, which means that I must be the square root of pi, which in fact it is. So let's create a pretty picture to visualize our hard work. So there's the Gaussian function with the shaded area, and that area is in fact root pi. So that is integrate change variables in a snapshot. So DSolveChangeVariables. Integrate change variables is marked as an experimental. I think, you know, there are certainly issues that need to be fixed, but I think we basically understand it. DSolveChangeVariables is very experimental, and I'll try to give you some hint of why that is. But it supports all the main flavors, so DSolve, DSolve value, and DSolve value. It tries to do a variety of techniques, which are all broadly changing variables. So reparameterizing the system, changing coordinate systems, separation of variables is also a form of that. So the old dependent and independent variables are inferred from an input DSolve expression, and that's already one hint of the complication. In integrals, we only have independent variables. Here we have both independent and dependent variables that we might want to be changing around. And again, changes can be specified as equations or coordinate transformations. So let's do a simple reparameterization. We have non-constant coefficient, but we'll do a clever substitution. And sorry, I skipped ahead. We do a clever substitution, and now we get constant coefficients because Q and P are just constants. Our variable was x squared. We have a nonlinear Riccati equation. We make another clever substitution, and we transform it into a linear system. That may not look very linear, but if I multiply everything out, we see we just have the dependent variable and its derivatives multiplied by the independent variable, which is the definition of a linear system. And this is a very cute example. I have an arbitrary coefficient, variable coefficient function here. And by a well-chosen change of variables involving an integral, I can transform it into the simple harmonic oscillator equation with, because A is a constant, and I just have the derivative, and the second derivative equals to 0. PDEs, I think, is where this really both shines and gets into trouble. So let's take a Poisson equation. So we have the Laplacian is equal to some function of the variables, and we'll go from Cartesian to cylindrical coordinates. And you'll notice again, I have a z tilde here so as to not be using the same variable name in both old and new coordinates. So now let's take the wave equation, which starts out with the Laplacian, and then you take 2 time derivatives, and again, try to transform it from Cartesian to cylindrical coordinates, and it yells at us, and it says Cartesian to cylindrical does not define a coordinate mapping in 4 dimensions. 4 dimensions? Well, I have 4 variables here. How is it to know which one of these is time and which one of these is space? That's that. Some people put time at the front, some people put it at the end. It's, so again, this is sort of where we're running into some issues and need to think through what's the correct design. So instead, I'll do this more by hand. I'll only transform the spatial coordinates. So I'll use coordinate transform to convert, and I've chosen to solve for the new variable, the old variables in terms of the new variables, which is why this is going backwards here. And then I just thread those to get me 3 equations, and voila, it works. But if we are doing this by hand, why don't we only transform the variables that are actually being changed? So here I don't change z and t. I only change x and y into r and theta, and I use polar coordinates to transform x and y. And this will, in fact, give me the same transformation. And how am I doing on time? I'm doing great on time. So I will I have this sort of funky looking partial differential equation. I will substitute in that the dependent variable is a product of univariate functions. And if I divide everything out, I get what's called separation of variables. I have one term only depends on one variable, a couple of terms that only depend on the other variable. They add up to 0. Therefore, they must be equal to each other, or as you change the variables, this equation would break down. And you go from this in order to compose the solution as a sum of solutions to these 2 separated equations. So potpourri, aka 13.2 series. So your basic Calc 2 topic, power series. So you can now say, instead of giving a sum up to some finite order, like, I don't know, 5, which sounds like a really big number to me, you can put in infinity, and it gives you as an inactive sum x to the n over n factorial, which is the power series for exponential. You activate the result, comes back to the original function. Some related power series, sine and cosine, which of course are just the even and odd terms of cosine of x by x. And we see our 2n plus 1 odd terms for sine and 2n even terms for cosine. Here's a Maclaurin series at a Maclaurin series of 1 over 1 minus c. And we added the option generate condition goes to true, which will give us the radius of convergence for our power series. So it converges as long as the absolute value is less than 1. Here's the Taylor series. So instead of doing it at 0, we'll do it at z equals 1. And we get what's really a sum from 1 to infinity. Might be nice if we could improve this answer a little bit, but it is correct. It's just, we don't need this piecewise. We just need to start the sum at 1. But again, it gives us the radius of convergence. We have to be within 1 of 1, or we must be 2. So we converge everywhere. We don't converge anywhere on the boundary except for the 1 point at z equals 2. Or at least we don't know that we converge. But I think in this case, we know that we actually do diverge. And Aram mentioned this, but I have time, so I will quickly go through this. We now use the method of undetermined coefficients and recognize recognize when we can use it to get simpler answers. So here's a new answer, and that's super simple. And we ask what the answer was in 13.1, and it's starting up, and it gives us, not a horrible answer, but clearly not quite as pretty as the previous one. And then we try a slightly more complicated forcing term, and that's pretty nice and simple. And that's a lot smaller than the previous one. And finally, we do a 4th order equation with a trigonometric driving term. We have really not too bad of an answer. We have some exponentials times an algebraic number plus some cosines and sines. And then we compare that with the old answer, which will take a couple of seconds to pop up. And it goes like that and like that. And so I think there's a bit of a difference between the old answer and the new answer. ImplicitD provides a general implicit differentiation function. I mean, basically it's D only, well, it doesn't necessarily actually solve, but it's sort of solving for you. Integrate the change variables and desolve change variables are a start on important use cases for changing variables. And we continue to refine our calculus support in every release. We will be having office hours downstairs at 3:30, so please come with your questions and comments. And I do have like a minute and a half left for any questions, if there are any burning ones. Okay, well, then let's just wrap early.